Dear students, welcome back to the course Introduction to Aeronautical Engineering. Today's topic will be horizontal flight performance. A typical mission of an aircraft looks more or less like this. The aircraft starts with a takeoff. Afterwards it will perform some turns and climb to its cruise altitude. Once the cruise phase is completed, it will descend. And finally it will land safely on the destination airport. Now, as you can see, a large part of the flight is horizontal flight. In this item today I will explain you how to determine aircraft performance in horizontal flight. Now there are 4 topics of relevance to aircraft performance in horizontal flight. We start with the minimum airspeed. On the other hand, we have the maximum airspeed, maximum range, or in other words, how far can an aircraft actually fly. And finally we have what we call maximum endurance, or in other words, how long an aircraft can stay in the air time-wise. Now, in all these situations, the aircraft is performing a quasi-steady, almost horizontal flight. In technical terms, this means, first of all, that the flight path angle gamma equals 0 and remains 0. And secondly, this means that the forward acceleration equals 0. Now, this greatly simplifies our equations of motion. Finally, for conventional aircraft operations, the angle of attack of the aircraft is fairly small, say up to 10 degrees, and the propulsion system is aligned with the nose of the aircraft. Hence the term cosine of alpha t can be assumed to be equal to 1 and the sine of alpha t can be assumed equal to 0. Now this leaves us with the most simple form of the equations of motion, which state lift is equal to weight and thrust is equal to drag. Now the next step will be to do performance calculations. Now for that purpose I have selected an interesting test case for you, the Spirit of St. Louis. This aircraft was designed in 1927 for a competition to be the first to fly across the Atlantic from New York to Paris. Now that may seem like a piece of cake nowadays, however back then it was a very challenging task. In fact, several people attempted to fly across the Atlantic and ended up paying with their lives. Now for the sake of this lecture, I estimated the lift-drag polar of the Spirit of St. Louis and its maximum lift coefficient. From the engine manufacturer, it's known that the propulsion system, a fixed-pitch propeller combined with a radial piston engine, could deliver a maximum of 236 horsepower at an RPM of 1800. Now let us start by making a performance diagram of this aircraft. Now the performance diagram of an aircraft is basically on the y-axis the power required, which is drag multiplied with airspeed, and on the horizontal axis it states the airspeed of the aircraft. Now we would like to calculate points in this graph and determine what the whole graph looks like. Now the pilot can essentially choose basically the airspeed, or in other words, the lift coefficient, because at each different airspeed we need a different lift coefficient. Now let's assume we're flying at a specific lift coefficient, and let's just start with CL max. Now in that case we can determine from lift is equal to weight that the airspeed equals the square root of the weight divided by S times 2 over the air density times 1 over CL, and in this case CL is CL max. Now all these terms in the equation are more or less constant. We can state that weight is constant, wing surface area is constant. We can assume we always derive this diagram at one specific air density. So this means that if we know what CL max is, we can actually calculate the value of the airspeed. Now on the other hand of the diagram, we have power required, which is drag multiplied with velocity. Now we already know the velocity, so we should calculate what the drag is in order to determine a point on the diagram. Now drag can be written as drag multiplied with lift divided by lift, because lift divided by lift of course, will be equal to 1. Now this is a little trick that makes our calculation simpler. And because we already have lift is equal to weight, I can state that this should equal drag divided by lift times the weight. And if we write out this equation, we get CD times a half rho V squared S divided by CL times a half rho V squared S times the weight. And you can see that all these terms cancel out against each other. So this leaves us with a fairly simple equation for drag. It's CD over CL times the weight, and in this specific situation I'm dealing with CL max. So the only unknown in this equation is basically CD, because the aircraft weight is a constant. So if we know what the lift drag polar of the aircraft is, and we stated that this is always can be approximated with a parabolic relation, then you can see that CD is basically a function of CL. And since we already took a specific value for CL, we can actually calculate the value of CD and write it out. Now we've determined CD, we have determined CL. If we know the aircraft weight, we can calculate drag. And finally, if we know drag, we can calculate what the required power is, since it is drag, which we already calculated here, multiplied with airspeed. So power required will be a specific value. Now if we know power required and airspeed, we can actually select the airspeed in the diagram, we can select the power required in the diagram and draw one specific point. Now we started off with CL max. If we want a second point on the diagram, we can simply assume that we have some other value of CL which should be smaller than CL max, and we repeat the whole calculation. And if you would do that, you would find another point on the graph and you would be able to construct all the points in the performance diagram and draw a nice line through it. Now, I'm not going to calculate all the points on this diagram at this moment. I've already done this for you for the Spirit of St. Louis, and that is what you will see on the next screen. Now, the complete performance diagram looks more or less like this. It looks like a typical performance diagram, but is it actually realistic? Now, the predecessor of NASA published the actual performance diagram of this aircraft based on obtained flight test data back in 1927 already. And as you can see, there are two lines now in the graph. It closely matches the results we calculated. So the line of flight test data and the calculated points are actually on top of each other. Now that is very nice, isn't it? So we can indeed represent the complete aerodynamics of a complete aircraft with a very simple parabolic relation and a constant, which is the maximum lift coefficient. Now to complete the diagram, we can plot the maximum power available as published by the engine manufacturer in the diagram. And in the next item, we will calculate the performance of this specific aircraft based on this performance diagram we just derived.